Okay, so our video deals with the fundamental theorem of calculus, both parts 1 and 2, and how it's used in real life in like natural sciences. And so what we're going to do is first take a look at part 1 and just what that entails, and then we'll go into some examples about how it can be used in science. So the fundamental theorem of calculus, part 1, says if f is continuous on open interval I containing a, for every value x on that interval I, the derivative of the integral from x to a of f of t is going to equal f of x. So pretty much the derivative of the integral will equal the function on the inside. So we'll see how this is used we'll start off with chemistry, and then we'll move on to physics. So if the concentration of a product in a chemical reaction can be found by the integral from x to 0 natural log 3t plus 1 plus 2 dt, find the equation for the rate of the reaction. So based on the fundamental theorem of calculus, which we see right here, derivative of the integral is equal to the function inside, we're going to be able to find the rate of reaction. So our units of concentration is going to start off by using molarity, and then what we're going to see finding the rate of reaction will give us our change in molarity per second, right? So what we can do here, just based off of what we have for part 1 fundamental theorem, we can see that the inside is going to be the function that shows us the rate of reaction, right? Because that's the derivative of the integral, and what's inside that just comes out at the end to be ln of 3x plus 1 plus 2 molarities per second. So now we're going to move into an example that deals with physics and electricity. So this question says the amount of coulombs that are created by an alternator can be found using the integral from root x to 0 of 1/4 sine 9t plus 2 dt. What is the equation that will give the current generated by the alternator? So this one, you might be tempted to just go in and do what we did in the last problem and say, oh, it's just the inside of the integral. But that's not quite true. This one's a little bit trickier than that. So what we're going to do is we're going to start off and define root x as u. That'll make things easier and help kind of show where we're going. And so what we're going to do is we want to find the current, right? And we know that the integral is going to give us coulombs. And current is measured in coulombs per second, also known as amperes, A. And so what we want to do is pretty much just take the derivative of the integral again. And so what's going on here, the reason we use u is because we actually have to use chain rule when we have something on the top, like root x. When it was x, using chain rule would just give us a value of 1 when we multiply by the derivative of x. So that's why we didn't really have to do anything in the first problem. But here, what we have to do is, once we define this as u, we can say f of u is equal to 1/4 sine 9u times u prime plus 2, right? Because using chain rule, we have to multiply by the derivative when taking the derivative. And so that means that f of x, once we replace it, is going to be 1/4 sine 9x to the 1/2 times 1/2, or 1/2x to the 1/2, right? Because the derivative of x to the 1/2 is 1/2 root x. And then plus 2, and that will give us our amperes. And so it's a really common mistake for people to not use chain rule and to just go in and be tempted to say, like, replace all of these t's with x's and call that the derivative. But really, you've got to use chain rule, and so that's why we use u. It's a very helpful way of kind of remembering that so you don't accidentally skip over.
The fundamental theorem of calculus also states that if little f is a continuous function on the closed interval a, b, and big F is the antiderivative of little f, then the area is the integral from a to b of little f dx, which also equals big F of b minus big F of a. The first problem gives us a graph of f prime, and tells us that the function value of 4 is 3. We want to find the function value of 12. To solve this problem, we can set up an integral. Understanding the fundamental theorem of calculus is crucial. You can set up an integral with the lower limit of 4 and an upper limit of 12 because those are the x values given to you. Then you're finding the antiderivative of the given derivative. According to the fundamental theorem of calculus, that integral is equal to the function value at 12 minus the function value at 4. In order to solve this problem, you must understand that the integral represents the area under the curve from 4 to 12, and in this case, that area is a semicircle. You can calculate the area of a semicircle doing 1/2 pi r squared. You can't forget to put the negative sign because the curve goes under the x-axis, making the area negative. From there, you can substitute values such as the radius, which is 4, and you can get that by looking at the graph. Additionally, you can also substitute in 3 for the function value at 4 because it is given in the original equation. Continue to solve, treating f of 12 as a variable, and eventually you'll get an answer of f of 12 equals 3 minus 8 pi. A very common mistake is not applying the fundamental theorem of calculus to this problem. Sometimes people may overthink it and might try to graph f of x from the given graph of x prime in order to visually find the function values at the given x points. Instead, all you need to do is set up an equation using the fundamental theorem of calculus. Additionally, while overthinking this problem, people might not realize that the integral of f prime of x is simply just the area of a semicircle. Additionally, it is common for people to forget the negative because the area is under the x-axis. To solve this problem, you first find the antiderivative, which is sine of x plus cosine squared x. Then, you apply the fundamental theorem of calculus and do f of 5 pi over 6 minus f of 0. After solving by substituting in correct values using the unit circle, you get an answer of 1/4. A common mistake is leaving off f of 0. Because sometimes in polynomial functions f of 0 comes out to 0, people often just leave it off since it makes no difference. But in this case, in a sine and cosine function, plugging in 0 for cosine actually yields a value other than 0, so it is necessary to not forget it. To solve this integral, you can put it into the calculator, which applies the fundamental theorem of calculus itself, and you get an answer of 147.015. To get to the integral, you press Math and go down to the 9th option, which is the integral. Then you just enter your boundaries and your equation to find the antiderivative of. Another way to solve this integral is by graphing. You can tell your calculator to set the lower and upper limits and it will calculate the area under the curve. Go to y equals and enter your equation, then graph it. You then press second trace to calculate the area under the curve, and you can set your own boundaries by entering the x values. As you can tell, you get the same answer. Scientists measure bacteria growth rate in millions using a function modeled by r prime of t equals 200 e to the 0.01 t, where t represents time and t equals 0 is 2017. What is meant by the integral from 1 to 15 of r prime of t? It is important to note that the integral represents the change in bacteria population in millions from the years 2018 to 2032. You can calculate the change in population by plugging this integral into your calculator and getting an answer of 3,035.682 million bacteria.
We hope this video has given you a better insight into how the fundamental theorem of calculus can be used in many different types of sciences, including but not limited to chemistry, physics, and biology. There's a lot of other uses for this too, but in the interest of time, we could only pick a couple. So, hope this has given you a better idea of how it can be used, and maybe you can use it in one of these ways yourself in the future.